With us here are three of the principals of the NASA JPL Voyager project, which this year won our Mechanical Lifetime Achievement Award. We like to give this award to machines and the people who create and tend to them that have, over their lifetime, sort of stunned us with what they can do and what they've discovered and what they've achieved. In the past, I think it was last year, we gave an award to the Mars rover, which outlived its projected lifespan by several years. And this year, we're looking at two space probes that have dwarfed the lifespan of the Mars rovers. The Voyagers were launched in 1977. And they were projected to have, correct me if I'm wrong, a 4-year lifespan. Is that correct?
Yes.
And they are now still sending signal back 35 years later. And they are just to put this in perspective, the furthest human objects from the planet Earth right now. They are the deepest things we have ever sent into space, and there is nothing that's going to catch up to them for the foreseeable future. They have on them information about the planet Earth and the people here and the life on planet Earth. They are, as things stand now, if ever a physical object makes it to a alien species, if there is one, this will be the first message that we've delivered out there to them, short of course, radio waves, which I guess we could get into. So with us here today is Ed Stone. He's a professor of physics at Caltech and a former director of NASA JPL, is that correct?
Yes.
Jet Propulsion Lab. Today we also have Suzanne Dodd, who I'm told call you Susie, is that right?
That's fine, yeah.
Okay, Susie Dodd, the project manager for Voyager, the current project manager for the Voyager interstellar mission, and Jefferson Hall, the Voyager mission flight director. And I wanted to split this into three sections. I'm going to try and keep them moving as fast as possible. I don't want to go over time here, but I'm going to split into three sections. One is on the history of the project. The second is on the day-to-day operations of it and just how we communicate and operate two vehicles that are so far out into space. And the third is on the interstellar mission right now. And what makes the Voyager probes newsworthy right now is that they are about to, well, at least we suspect, they are about to or may have already crossed the heliopause. And I could attempt to tell you what that is, but I would rather start with Ed Stone. And why don't you explain to me what the heliopause is and why it is significant?
Well, the sun has a 1,000,000-mile-per-hour wind blowing radially outward from it in all directions. That's the solar atmosphere just expanding out into space. And that expansion creates a huge bubble around the sun. And up until now, all the spacecraft have been inside the bubble. All the planets are well inside the bubble. Voyager 2 now is 122 times as far from the sun as the Earth is, and is right at the edge of this bubble, about to enter interstellar space.
Voyager 1.
I'm sorry, Voyager 1, about to enter interstellar space. That is to leave the solar bubble behind and enter into the material which is outside, which has come from the explosion of other stars in the last 5 or 10 million years ago. So it's a major milestone in human exploration once we leave the bubble.
I'll start with a few questions about the history of it then. So in 1977, the Voyager project, the Voyager probes were launched in 1977 because of a rare planetary alignment that was going to happen that year and not for another 176 years. So what was the nature of this multiplanetary episode? When was it discovered, and did NASA pick up on the urgency immediately? And you've been with the project the longest, right?
Yeah.
So I'll let you, in fact, since 1972, is that
Yes,
correct?
that's right.
So I'll let you speak to that.
Yeah, it was 1965 when a graduate student from Caltech was working at a summer job at the JPL, and his job was to look for opportunities to fly by a planet and use the planet's slingshot effect to speed the spacecraft up. And what he discovered was that if you launched a spacecraft in 1977, Jupiter, Saturn, Uranus, and Neptune were all on the same side of the sun in just an orientation that a single spacecraft could fly by one after the other and fly by all four. And it was then just a 12-year journey to Neptune rather than 30 years. So it really did make a huge difference in the possibility of exploring all of the giant outer planets. Every 176 years, this alignment happens.
And how prepared at the time was NASA for this sort of mission?
Well, this was 1965. It was hard to get even to Mars in 1965. Not all the missions worked. So this was a bold step. But in fact, there was a plan to develop a very special spacecraft which would have a high probability of operating for 12 years in space. Remember, the space age itself was still very young. And that was decided it was too expensive. And in fact, instead of that, it was opted to go with what was called the Mariner Jupiter-Saturn 77 mission, with a goal of just a 4-year mission to Saturn, but launched in 1977 so that if everything was working, we could step by step complete what was then called the Grand Tour.
Let me switch to Susie and Jefferson for a moment. Describe the type of equipment that's on board the probes. What's on it? What does the equipment do?
Well, there are originally, is it 10 or
11
instruments. I believe 5 of those were like camera-type instruments. Mm-hmm. So two cameras and infrared spectrometer, photopolarimeter,
a UV spectrometer.
and a UV spectrometer. So those particular instruments were used to take images of the planets. Those instruments no longer operate. They could operate, but there's nothing for them to look at. They were designed to look at the planets. We also have a suite of instruments that we call fields and particles instruments, and they're out there just sensing the environment of space. And those are the instruments that are operating right now. And so this is all early 70s to mid 70s technology. One good data point I like to tell people is that in 1977, the Apple II computer came out. So that's the technology that Voyager was just slightly older than when it launched. So it doesn't have a lot of memory. Something on the order of 30,000 words is what I was reading, which is about a half a megabyte. Not a very good image from your iPhone. That's about as much memory as a spacecraft has. But I think somewhat the simplicity of it and then the redundancy that was built into it has made it last as long as it has.
Now, Jefferson, I know that and we had talked earlier, and you had mentioned that you had been involved in, I think, the Apollo program before this. Is that correct?
That's correct.
So how would you contrast the two types of missions? How long have you been on the Voyager mission?
Well, since '78.
Oh wow! So you've been part of two very iconic moments in the American space program. How do you see the two?
Well, I wasn't really that close to the Apollo program. I was helping test the Saturn II second stage down at Seal Beach, California. So I really wasn't involved in the operation of anything on the Apollo program. Whereas on the Voyager project, I've been involved in various phases of operation, from sequencing to spacecraft operation, et cetera. And it's very interesting, and it's been very rewarding. And what's really interesting about the mission now is that we're in a region where no one has been before, so it's new science. So it's very interesting to see what's out there. There's no models, no predictions. Is what we're going to see. So it's very interesting to be able to see in my lifetime what's beyond this transition.
The Voyagers have both a scientific as well as a cultural mission. The Voyager program famously worked with Carl Sagan to produce the Golden Record, which is, I won't get into all the details of it, but it's pretty fascinating. It has everything from sort of various music from around the planet. It has images. It's got messages from world leaders at the time. What was it like? This was sort of Carl Sagan's pet project that he really sort of put forth to to use these probes as a message to the universe. What was it like working with him, and what was how do you sort of reconcile the dual nature, the scientific and the sort of cultural missions of Voyager?
Well, Voyager is, after all, more than just a science mission. It really is a mission of exploration. It's sort of related to many missions of discovery, both seaworthy and even further back than that. So I think that Carl Sagan designed some plaques for Pioneer 10 and 11, which were the first spacecraft to fly by Jupiter and Saturn.
Those are with the humans sort of
Yeah,
waving?
that's right.
Yeah.
But that was just a plaque. And then John Cassani, who was the project manager of Voyager at the time, or just before launch, asked Carl if he would be willing to design a similar thing for Voyager. His team decided they could do better than just a plaque. They could actually create a 16 2/3 RPM grooved record, double-sided, which would have on it these images of Earth, greetings from 55 languages of Earth, music from all the many cultures on Earth. And I think it was really a time capsule, basically, of this is the place that finally could send such a message to leave the sun forever. These spacecraft will never come back. They will orbit the center of our galaxy along with all the stars for the next billions of years. So a little bit of Earth will, in fact, be in orbit around the center of our galaxy.
You've got no way of getting it back? All this engineering and you didn't find a way to get them back?
No.
I understand that the record actually has it comes with a needle, is that correct?
Comes with a phono cartridge,
Just in case
yes.
they don't have a record player. So the Voyager spacecraft has taken some iconic images of obviously all the four gas giants that you mentioned, Jupiter, Saturn, Uranus, and Neptune. All of you have been involved at some stage where you've been involved with an encounter with a planet. Is that correct?
Yes.
I'm just curious how it feels when you know that the how it felt anyway when the spacecraft was approaching a planet and you knew that you were about to actually, I guess, engage another planet in the solar system closer than any human, I guess, closer than any human or human machine had ever managed to do. How does that feel amongst you and your colleagues? I guess I'll work down the line.
Well,
start with you, Ed.
it's certainly, science is often something where there's a return that comes periodically over a period of years, but these encounters were quite different. We really started on this mission in 1972, launched in 1977, and during all that time there were no scientific discoveries. The first discoveries came in 1979 with the first Jupiter flyby, and then they came in a flood. So it was really remarkable. Each day we were seeing things that no one had seen before. The next day we saw still more things at even higher resolution. So every day it was a day of discovery. It was really quite a remarkable experience as a scientist to see so many new things so rapidly in succession. And things we hadn't even thought we would find. We hadn't even thought about the possibility of it.
What's a good example?
Volcanoes before Voyager, there were only known active volcanoes in the solar system were here on Earth. And then there's Io with 10 times the volcanic activity of Earth. Here on Earth was the only known water oceans. Then you see Europa, which had an ice pack on it just as though it had an ocean. The only known nitrogen atmosphere in the solar system was right here on Earth. And after we flew by Titan at Saturn, there was a moon which had a nitrogen atmosphere 60% more higher pressure than here on Earth. Just time after time, what I call our terracentric view suddenly had to be greatly expanded. And that happened day after day in planet after planet, and it's still happening as we're entering interstellar space.
And Susie and Jefferson, from a technical and operational point of view, what do you like? I know that a lot of the systems have to be automated by the very nature of them, but as you're preparing for this, as you're dealing with things like how to do imagery at a distance like that, how to even know that you're looking at the right thing, how does that work?
Well, we did, I came on Voyager before the Uranus encounter. It was my first job out of college. As a matter of fact, I had a couple different opportunities, and I chose to work on Voyager because how many other spacecraft are going to send to Uranus and Neptune? Big goose egg here. It was very exciting to get on the project. It already had the history of the Jupiter and Saturn flybys and discoveries, but Uranus and Neptune were a little bit of a different animal because they're both much further out. So the light, when you're trying to take pictures, the light is a lot fainter. And in particular, and there's less known about the orbits, the mass of the planets. They were kind of fuzzy little blobs, I think, that the Hubble Space Telescope had taken a few pictures of. So in particular at Neptune, I was working in the sequencing area, and we made a lot of adaptations to how we did sequencing to adjust for the low light levels and the unknowns in the mass. We didn't know exactly where we were going to fly by the planet because we didn't know the mass and what the gravity effects would be on the spacecraft. So we developed a system where we had something called a movable block. And it took, I'm trying to remember the one way, it took how many, maybe 5 hours to get commands back at Neptune? Anyway, it took a while to send the commands to the spacecraft all the way at Neptune too, because it's just so far away. But so basically what we did is we created a sequence so that the most critical portion could be shifted in time without running into the portion around it. So we put margin on the most critical portion of the sequence. And then I think probably in Jefferson's area, they developed image motion compensation where they actually slewed the spacecraft with the motion of your image. It would be like trying to take a picture out of your car window, and you need to pan it to keep it on the same object. That's essentially what we did at Neptune too. So those are, that gives you an example of some of the engineering adaptations we did for the outer bodies of the Grand Tour.
And Jefferson, describe the propulsion system on Voyager, on the Voyager probes. The way I understand it is that it's like incredibly fine-tuning. It's very, very low power. You're trying to do tiny adjustments here and there. Is that right?
Well, now we are, because we're not doing trajectory change maneuvers anymore. So we have thrusters on board that just fly, to keep the spacecraft oriented, okay, and also keep the high gain antenna pointed to Earth, so we always maintain communication. So currently we're not using a whole lot of fuel because we're not really firing, a lot of pulses, okay? So we use on the average, maybe 5 kilograms of fuel per week or something like that. Now we are doing more maneuvers on Voyager 1 that's causing us to use additional fuel, but, fuel is not an issue as far as, lifetime of the mission. That's,
We have something like 60 years.
60
fuel
plus
left,
years of
so
fuel left because we don't use very much.
Fuel is not
okay?
the limiting resource.
Power is a limiting resource. Okay, the RTGs, the radioisotope thermal generators, which generate power for the spacecraft, we lose about 4.3 watts per year. Okay, we currently have about 268 watts remaining on each spacecraft. Okay, so we have to manage the power very closely. Okay, to make sure we always maintain a margin in the event something happens unexpected. Okay, gyros come on, or you have some kind of an unplanned maneuver or something like that. So we have to really maintain our resources, and that's really the big job right now is making sure we have enough resources. We anticipate having enough power to last until about 2020, possibly 2025, operating the current suite of instruments that we have on board. Around 2020, we anticipate having to start doing power sharing, meaning turning an instrument off for a period of time, alternating on and off between instruments, but that hasn't been determined yet. But that's what we think we have to do.
Yeah, and I want to get back to the nature of the power source because it's rather interesting. But before we go there, I wanted to ask one more thing about the propulsion systems and just how you engineer this how the gravitational slingshot works, and just what the sort of the mechanics of it are, both from a sort of gravitational standpoint, but also from a propulsion standpoint. How much engineering are you doing as you're going around the planet, or do you just steer it in and let the planet sort of take its course? How does that work?
Well, the gravitational slingshot effect just comes from the fact that the planets are orbiting the sun, therefore they're moving. And as the spacecraft flies by and turns a corner, it picks up some of that orbital motion. Mm-hmm. And so, in fact, we got as large a change in spacecraft speed when we flew by Jupiter as we got from the launch vehicle in Florida. So it's as though one had an entire launch vehicle, virtual launch vehicle, propelling the spacecraft, giving it a large boost. When we launched Voyager 1 and Voyager 2, we did not have enough energy to get even to Saturn. We got that energy at Jupiter. It gave us a big boost and sent us on our way, and then Saturn gave us another boost. And the net result is Voyager 1 is the fastest thing leaving the solar system at 17 kilometers per second, about 38,000 miles per hour.
How does that compare to like a comet?
Oh, comets have comparable speeds, but they're coming in. In fact, the Earth is moving 30 kilometers per second around the sun. So Voyager is moving half as fast as the Earth is moving in its orbit around the sun, basically. That's another way to think about it.
Interesting. So,
Comets have a comparable speed.
So now let's get back to the power source, because it's really fascinating. When we think of how you power things in space, we often think of satellites, for instance, that often use a PV-based energy source. But obviously, when you're thinking about a deep space probe, that you would swiftly lose any benefit you would get from a solar array. So you engineered a system that is both sort of fascinating in its complexity and simplicity at the same time. So how does it work? And whoever wants to weigh in on this can.
Well, it's a very simple power supply. It's the natural radioactive decay of plutonium-238. That radioactive decay heats the material to about 1,000 degrees, and you bolt thermocouples on the outside of the hot source, and you let the cold outer surface of the thermocouple so that it generates electricity. So it's a very robust, simple power supply. The half-life of the radioactive material is 88 years. So that means 88 years later, you have half as much activity, half as much power. And as Jeff said, we know very precisely that we lose about 4 watts of power per year. And that means we can predict fairly accurately when we'll have to turn off our first science instrument and when we'll probably have to turn off the last one.
And so you're obviously operating an antenna with that power source right now, and obviously it has to be a relatively weak signal to operate off of that.
20 watts.
Now describe
your refrigerator light bulb, basically.
So describe what we have on Earth to receive that. What do we need on our end to receive a signal that weak?
Well, we have 3 deep space networks around the globe, okay, that track the spacecraft. One's in Madrid, Spain, one's in Canberra, Australia, and one's in Goldstone, okay. The Voyager spacecrafts are sending data down 24/7. Now, we don't track it 24/7 because we're in competition with other missions that want part of the DSN resources as well. So we get on the average maybe 5 to 6 hours per day per spacecraft, okay. So whenever it's time for us to track the spacecraft, and we can capture the data being sent down from the spacecraft. Okay.
So most people in this room have probably never known a computer to work reliably for more than 7 years.
How about 7 days?
Yeah.
So you had to, in 1977, or I guess in 1972 when you first started engineering this, come up with a computer or a series of computers that you hoped to last for 4 years, and they have now lasted for 35 years. I guess I'm in sort of disbelief that this is even possible. But describe the computers on board Voyager and on board the 2 Voyagers, and how are they engineered? What can they do? How do they compare with a modern cell phone?
Susie?
I'll let Jeff describe what they do. But the comparison with take a 4 gigabit iPod, which is old, about the lowest level of memory you can get these days. The memory on Voyager is 100,000 times less than that. So I think there's something to be said for simplicity as far as longevity, kind of like your cars. But I'll let Jeff describe the computer
There are
system.
basically 3 computers on each Voyager spacecraft. One for the attitude control system, which controls the maneuvers and the pointing. It has control law to respond to various things that the spacecraft may do. You also have what's called a flight data subsystem, which in turn processes all the data being sent to it from the science instruments, et cetera, and then transmits it to the ground. Then we also have the command computer subsystem. This is a computer that actually sends commands to the various instruments, subsystems, et cetera, on board the spacecraft. Now, on Voyager, we have each spacecraft has a background sequence running continuously. This sequence contains periodic calibrations and maneuvers, et cetera, that we want to run to the end of the mission. Okay. Now we do augment that every 3 months with overlay load that would put additional activities in. If you want to modify the memory, or if you want to do an additional maneuver, do an additional playback, then we send these commands up to tell the spacecraft to do that. And it's all controlled by the command computer subsystem.
And I'm told it has an 8-track tape on it?
It does. It has an operating 8-track tape
Yeah,
recorder
right.
that we use. We record some high rate data, and then we play it back every 6 months. So it does have an operating 8-track tape recorder. I don't know how that's lasted so long, because my car 8-track tape recorder went right away. Broke right away.
But one thing we do with the tape recorder, we periodically do what's called tape recorder maintenance. What that means is we slew it from one end to the next to make sure it doesn't stick in one place, okay? And sort of keep the lubricant moving around. So we do that periodically so it doesn't stick, Because spacecraft have had problems with, if you don't use it enough, then all of a sudden you lose, the ability to record in certain areas of the tape. So we move it periodically in addition to records and playback to try to make sure it doesn't stick in one place. Or we don't lose the ability to record in a certain place.
Yeah, I have to add that the engineer who is responsible for the tape recorder has been with the project almost as long as Ed has. He's halfway retired, but he still likes Voyager so much that he's working. But he's probably the only one, if you tried to find a young engineer and you told him, you're going to be responsible for the 8-track tape recorder, they would just like look at you and go, what?
Yet the engineer you're talking about still has a series of 8-track tapes along the floor of
floor of his office,
right?
yes, his car, that's true, yes, exactly.
Now, what about the, I want to dwell on the equipment for a little bit longer and then get into the nature of the interstellar mission. What about the imaging device? Imaging is one of those technologies that has obviously advanced by leaps and bounds, and you're dealing with sensors today that could do 20, 25 megapixels. What are the optical sensors on board Voyager and sort of obviously they've been disabled now, right?
Yes, they have.
Yeah.
Each spacecraft has Vidicon cameras on board. The narrow angle camera is 1500 millimeter focal length. The wide angle camera is 200 millimeter focal length with an f-stop aperture of f3.5 for the wide angle and f8.5 for the narrow angle. Okay. Now the Vidicon has all the electronics to take pictures and do the analog to video conversions to turn it into an 8-bit digital word, which gets sent to the FDS. The FDS reads this data out and transmits it to Earth, okay? And the FDS program had imaging data modes in it, so if you want to record, various pictures in different data modes, you can switch to it. Each Vidicon has 8 filter steps for exposure control. That's all controlled by the flight data system, so you can take pictures of various filter wheels, because it commands it to step to various positions and stuff like that. The cameras have been turned off. We don't have power to operate the cameers anymore.
And there's probably nothing close by to take a
Yeah,
picture.
No,
exactly,
right.
yeah.
Now, the last picture, though, that was taken, if I recall, was another of Carl Sagan's influences, and he asked to use some of the power to turn the craft around, correct? And
No, not quite.
describe what it was.
This
It's called the
family portrait.
The family
Well,
portrait.
family portrait. We did this in 1990. Remember, our Voyager 2 flew by Neptune in 1989. So this was after the end of the planetary part of the mission, before we turned all the cameras off. Voyager 1, which had passed by Saturn in 1980 and was on its interstellar mission phase already, we just turned the cameras to look back toward the sun. The spacecraft itself always points at the Earth, so the spacecraft didn't turn. We just turned the cameras around to look sort of toward the sun, which we normally don't do. We didn't look exactly at the sun because at that time you could see essentially all the planets from beyond all the planets. So this was the first time we'd had a camera that we could actually take an image of the planets in the solar system from outside the planets. We were still inside the bubble, but we were out beyond Neptune. We were beyond all the planets, and we were beyond Pluto.
And if you haven't ever read it, Sagan wrote something called The Pale Blue Dot, based on this photo, which gives a fascinating bit of perspective on life on Earth and sort of the relative nature of that to sort of the vastness of space. And I won't even dare paraphrase it now, but if you get a chance, read The Pale Blue Dot, and it's a short essay he wrote on it that really is quite humbling. So now let's get back to the heliopause and why this is significant and why we believe that this next, what we are planning to learn or what we expect to learn from this next phase of exploration. What do we know about the heliopause now, and what do we expect to find once? How will we know when we've crossed it, and what do we expect to find outside of it?
Well, inside the bubble, the wind comes from the sun. The magnetic field is the solar magnetic field carried out by this plasma wind. Outside the bubble, the wind is from other stars which blew up as supernovae 5, 10, 15 million years ago. The wind is from these other stars. The magnetic field is an interstellar magnetic field, not the solar magnetic field. Outside the bubble, there are things called galactic cosmic rays. These are nuclei of atoms that have been accelerated up to half the speed of light, and some of which, if they're fast enough, can actually get into Earth, and that's called cosmic radiation here at Earth. But the slower of those are outside, can't get inside the bubble. So once we're outside, we will, for the first time, know what the intensity of the radiation is outside the bubble. The bubble serves as sort of a shield against some of what's outside. So we'll measure the cosmic ray nuclei which are out there. We'll measure this magnetic field. We have some ideas, but we need to measure it because it is distinctly different than the magnetic field inside, and that will be one of our signatures of whether we're inside or outside. So that this will be our first exploration of this space that's between these spheres that each star have. And that's the reason it's called interstellar space.
And what about how would you? Obviously, we're getting detections. Well, not obviously. We're getting readings back now that seem to indicate that we're on the threshold of something, right? So, how do you interpret those? What do you make of these? How would you know? What's the definitive answer? How can you say, all right, we've now crossed the heliopause. We are now in interstellar space. What could you read? Where do you? Who hands over the sheet of paper and says we've done it?
I'll tell you. I will tell you what we think we know today, and after we really finally discover it, then we'll know what we didn't know, right? Okay. So what we think we know is that the galactic cosmic rays outside that can't get in. Once we get out there, we will see their full intensity.
Okay.
And in fact, they are higher now than they've ever been. So that certainly suggests either we're out there already or we're getting very close. In addition, there are some energetic ions which maybe move at only 10% the speed of light, which are actually created inside the heliosphere itself. Once we get outside, they should be gone because they're sort of trapped inside, and once they get outside, they will zip away. So we should see higher galactic cosmic rays, we should see lower energetic particles from the inside, and the magnetic field, which inside is from the sun, should be different when we get outside in interstellar space. And so what we're seeing is a change in both the particles, which suggests we are getting very close and we will really do need to look at the magnetic field to decide whether we're still inside, just connected now well to the outside, or whether we're actually outside. We don't know yet because no spacecraft has ever been there before. And this interaction between our sun and what's outside is very complicated.
This is, I wanted to shift gears for a second because Ed and I were talking about something just before this panel that sort of blew my mind a little bit, and I was just curious about it. I just wanted to discuss it here. Is it possible that that either the Voyager probes or any of the other probes we send out into space are actually carrying microbes or life of any sort on them?
Well, I think the Voyager spacecraft were not sterilized, so there undoubtedly are, there may well be various kinds of spores
that could survive interstellar space?
That could survive interstellar space for some period of time. We know that these can be very rugged organisms. But of course, Voyager never really got close to any planet even in the solar system, and now it will, the closest it will come to another star in 40,000 years. It will be close to another star, close meaning only 1.6 light years from the star. That's how close it will get, no closer.
Yet there is the possibility, the distinct possibility, that we have actually sent biology from Earth outside the solar system.
Well, I think we certainly have done that. I think it's on the spacecraft. Yeah.
Interesting. And Ed mentioned that apparently they do sterilize the Mars rovers before they send them out for fear of contamination.
Viking we did, not the subsequent ones.
Oh, okay.
Only Viking was sterilized.
So if we're searching for life on Mars and find it, it could well be that we put it there ourselves. I wanted to get briefly into the communication that goes on. So Voyager 1 is now 11 billion miles from the sun, is that correct?
That's
I know
correct,
that it's
yeah.
a little further every
Yeah,
day,
yeah.
obviously. How long does it take to communicate with Voyager 1? Why don't you guys tell me about that? Maybe Jefferson, you could tell me.
Well, for Voyager 1, it's approaching, I think,
Yeah,
17
it's
hours.
almost 17 hours, yeah.
One
And,
way.
One way.
Okay. And Voyager 2 is about 14 hours or so one way.
Wow. And so that means that as far that just to get a command and confirmation of the
It's
command.
like a day and a half. I always like to tell people, I go to my office Monday morning, I send a command that says, "Hi Voyager, how you doing?" And I work the whole day, go home, sleep, come back the next day, and sometime in the afternoon, Voyager says, "Hi, I'm here. How are you doing?" And that distance really changes how you plan what you're doing. A Mars mission, the Curiosity rovers, are anywhere from 10 to 20 minutes. Okay, we're looking at 14 hours, double that for round trip. Right now with Voyager, a lot of things on board are autonomous. It's basically the spacecraft has been programmed to keep operating if it doesn't hear from us. And it sends back data all the time. So it will operate and send back data even if it doesn't hear from us.
I think one thing that's often forgotten is the Voyager spacecraft were the first fully automated spacecraft sent out to deep space. They fly themselves because of exactly this problem. You cannot, in fact, control the spacecraft in real time. The spacecraft has to fly itself. It's the first spacecraft that had built-in failure algorithms, so that if something went wrong, it would go into a safe state, protect itself, waiting for commands from back home about what to do next. We have now on the spacecraft a very tiny little program, which if we never send them another command, they will continue to point at Earth as long as they have electrical power, and to transmit to Earth as long as they have electrical power, with not another single command being sent.
So what would it take to mount another interstellar mission at this point? And I guess there's sort of two elements to this, which is the political aspect of it and the technical aspect of it. Now, you guys benefited from the alignment of the planets that allowed you that slingshot. Obviously, you could send something directly to Jupiter and maybe get that much of it, right? But
yes.
As you mentioned to me, you can throw something out into space, but without enough propulsion, it's going to come back, right?
That's right.
It becomes it has a solar orbit.
Right.
So let's start with the technical aspects of it. What would it take to technically launch something into interstellar orbit right now if we decided to do so?
Well, one could do something like that with using the current largest launch vehicle, the Titan IV, and using an RTG, radioisotope thermoelectric generator. If you had a kilowatt of it instead of 400 watts, which we have on Voyager, and an ion drive, that would help. You could probably get out there twice as fast as Voyager has with basically current technology, but only twice as fast. So it means that it's taken us 35 years, and it would take another, even the most advanced spacecraft that we could do today, half that long to get where Voyager 1 is today. And that's a very long journey. And obviously we had the advantage of having those planets, which were the important initial phase of that journey. We were doing science in the first decade and a half just on the planets, and now we're 3.5 decades finally reaching the edge of interstellar space. We'd like to go well beyond. Voyager will not get very much beyond before it runs out of power. We really won't know what the space is except right outside of our bubble, but that's what we will learn. And eventually, someday, some decades from now, our technology will allow us to get out there much faster so that we can go well beyond what Voyager will be able to do.
And Susie, why don't you speak to the political aspect of it? What would it take to sort of get the funding and get that type of thing get it started?
It takes a long-term commitment, which is hard to get out of the federal government because they're up for election every 2 years, so they want a result in the time that they're in office. I was just thinking, Ed, maybe you would want to, slingshot it around Jupiter a few times to gain some speed and take a few pictures, and that would help fund it if you actually flew by another big planet on the way. I think Ed might be able to speak better to this, but there's the time period on Voyager between the end of the Grand Tour, like the start of 1990, and before Voyager crossed the termination shock in 2004. That's 14 years of just flying through space. And every year your budget gets cut. Every year they ask you, why are we paying for you? What's the science you're doing? You know, and every year we say, we're getting closer, we're getting closer. But Voyager went through practically a cancellation review, I believe, right
Twice,
around 2000,
right.
yeah.
Yeah,
So
2001.
it was hard to keep this project going when there wasn't a planet you were flying by or you know, an immediate encounter with something new. It was hard to keep it going. So that's really the political challenge.
Yeah, and I think also from a scientific point of view, there are only so many missions that we can do, obviously. And a mission like Voyager, an interstellar mission follow-on, would be competing with another planetary mission of some sort, another Mars mission, for instance. And so that's the trade-off that always has to be made, because one can only do a few of these things per decade.
Now, personally, I'd like to see something go to Uranus and Neptune again.
Yeah, and
maybe on its way to interstellar space.
Yeah.
But you know, I don't see any of those missions anywhere close to being even in the early phase A development stage.
Okay, I want to take just 2 questions from the audience, then I got to wrap it up. So does anybody have a quick question?
I would be curious to know a little bit what is the story behind the team from 72 to 77. What were the resources that were mobilized internally in NASA from the contractors? What were the different disciplines that were covered by the team? And ultimately, what were the challenges to keep all of this team together?
There were a whole series of questions there.
I think you're talking about the development before launch,
Yes.
right? The teams, yeah.
Well, yes, this was by the way, between 1972, the official start of the program was June of 72, and we launched in August of 77. 5 years to develop a totally automated spacecraft that had never been done before. So it was about as much as one could reasonably expect to have happen in that 5-year period, and 2 of the spacecraft. The total cost at that time, I think, for the spacecraft was something a little over $250 million in those year dollars for these 2 spacecraft. And the team was not only an internal JPL team, but a number of course, subcontractors that were providing the various subsystems, the traveling wave tubes, the radio transmitter itself, for instance. There are a number of subsystems which were being produced by contractors working with JPL. But JPL had the overall responsibility for the system design, for integrating and testing it.
Yeah, I'll tell you a little interesting anecdote is every once in a while I get a call from a contracting company and said, you know, our company built those thrusters that are on your spacecraft still working 35 years later. Can we do a press release about it? You know, and sure,
that's right.
It's yours. You want to advertise that it's still working. Great, go ahead.
One more question, and then I'd like to open it up to more, but we've got to get the next panel on. So, Dova?
Is there a triage to when you turn on like the science instruments? I know the cameras are turned off now, but is there sort of like a
hierarchy?
Well, we haven't really worried about that in detail because it's still about 8 years before we think we'll have to turn the first one off. And other things could happen between now and then, which would, maybe an instrument might fail. Something else might fail on the spacecraft. So rather than worrying about exactly which one would be first, we've decided it's just easier to wait until we're closer to the time when we have to do it. And we'll also be in interstellar space almost certainly by that time. And that will also may change the priority as to which instrument is left on the longest. But ultimately, the instrument using the least power will be the last one on.
Okay, I want to say thanks to my panelists here. This is a fascinating discussion, and thanks to all of you for attending. And as with all of our panelists, please feel free, unless they're, I don't know, very, very shy, which I don't think they are, to approach them during the rest of the day and ask them any questions. So we'll end that here. Thank you very much.